Last speaker of the day is Professor Gianluca Piazza, and he is also going to speak about nanomechanical systems, nano-electromechanical systems, in particular the piezoelectric types. He is currently at the University of Pennsylvania, but not for long. He is going to soon be at Carnegie Mellon. He'll be an associate professor there in the electrical and computer engineering department, and he's a longtime DARPA researcher, or DARPA-funded researcher, I know that, in the area of MEMS and NEMS, and he'll give us a talk about his work in this field of energy reduction. That will advance, yeah, or here.
Perfect. All right, good afternoon. Thanks, Dan, for the introduction, and thanks to the organizing committee for inviting me to present the work that we've been doing at the University of Pennsylvania on actually a piezoelectric NEMS approach to low switching voltages and few kT switching energies. So a brief outline of the talk. I won't spend too much time. Sujay King has already set the stage actually for mechanical computing. It's a completely different type of more aggressive approach, probably a long-term approach. And then on the other side, specifically instead talk about and convince you that this piezoelectric approach is an interesting solution for making what we call mechanical transistor. And then some example of at least small-scale integration. And then some of the problems we're working on now, which is the scaling of the switches, making miniaturizable and making really a low-power solution, and then wrap up with some concluding remarks. So the problem is the power, right? The power challenge, and in particular this graph highlights actually how the passive power density keeps increasing with the scaling of the nodes, and in particular the fact that it becomes comparable to the active power, so that's due to leakage. And actually talking to a colleague at the University of San Diego who works on RSMN switches, who actually tried to dissuade me to actually work on this project, was telling me that nothing will replace silicon, and the answer is correct, actually. Nobody will replace silicon. Better, nothing will replace silicon. Better, we have fact replacing silicon with an air gap there, right? We're removing the silicon so that then we don't have leakage. But the impact of the mechanical switch, I think, is beyond just removing leakage. It's really about lowering switching voltages. Is the fact that you're using a new physics now, completely new physics to switching, you're going basically to reduce that subthreshold slope, and now you can swing around, as Professor Sujay King already highlighted, with a very low delta V. Basically, you can move around, and from another source, this was already acknowledged back in the days, probably in 2007, not the best measurement were done on this subthreshold slope. We have less than 0.1 millivolt per decade nowadays. Many researchers have reported that. And it's definitely possible. So this is sort of just to state the two key reasons to pursue basically this mechanical approach: low leakage, low subthreshold voltage, and low swing voltages especially. So our team at the University of Pennsylvania has been looking substantially at producing these mechanical elements, devices basically that are used based on piezoelectric approach on aluminum nitride material, and a particular type of design that I'll go in detail. And then the use of arrays, small arrays, and then in collaboration with Rob Karpik and Deon, looking also at a problem of counter-reliability, as well as a new architecture that sort of try to work around the problem of reliability of the switches. So what is our approach? We're using basically aluminum nitride as the core material, as a piezoelectric material, to make a mechanical transistor. And here's an SEM picture of one of the mechanical transistors that we've implemented. There's absolutely no difference in terms of terminals from a regular semiconductor transistor. We have a drain, a source, and a gate, and a body. So essentially, for a digital circuit designer, it looks exactly the same thing. There's two things that I want to point the attention to, though, is not just a black box. It's a black box with a slightly different transfer function with a regular switch. You have a body terminal that works slightly different than the one of a semiconductor transistor, and I will show you how we take advantage of that actually to lower basically the switching voltages. And then the other thing is that basically you don't have overlap between the drain and the gate and the source and the gate, which allows you to play substantially with the new topology, a new solution when you're doing computation. And effectively what we have is a source and drain that are mechanically connected by a set of actuators that you see here. Effectively there's two beams that are moving up and down and are closing the contact. So how does it work? The principle of operation is relatively straightforward. Basically, we're using what is called the D31 mode of actuation of piezoelectric. So by applying an electric field across the piezoelectric material, you get an expansion. In this case, we're getting a lateral expansion. Of course, a lateral expansion doesn't buy you much in terms of opening and closing, so you need to engineer the device. We're stacking, basically, piezoelectric layers on top of each other so that we can offset the neutral axis with respect to the lateral displacement. If you do that, effectively, you can actuate it as a unimorph, but more effectively as a bimorph by applying, basically, by reversing the polarity on the two electrodes. And effectively, you're getting a bending moment because one layer wants to stretch and the other one wants to contract. So that's how we get the piezoelectric actuation in the out-of-plane type of mode for this type of devices. So you notice also that we're using two beams. Why using two beams? Effectively, we're wasting more area. The problem is that when we're scaling this geometry, when we're going to nanoscale films, we have a problem with stresses. And in particular with the fact that we want to maintain a very, very tiny gap over relatively large mechanical geometries. So if we release only one beam, effectively, your gap becomes uncontrolled. It's not anymore controlled by your film thickness. Instead, simply if you release both beams, you're getting basically almost a constant gap. The best solution is, of course, put the two beams next to each other, and that's what we've been doing in the more scaled type of solution. And you can see that we have still our basically source and drain connected through that little tiny contact, and then a gate and body terminals available. Basically, it's the same two geometry that I showed you before, but now parallel to each other instead of facing each other, which allows more control, effectively, of the gap. So this is sort of ultimate stress mitigation. You can see that, in fact, we're suffering, given the length of the beam, from a lot of basically curvature there, but the switch is still functional thanks to this type of solution. The other thing that I pointed the attention to was the body bias. Right? I said that we're basically deviating from what is the standard actuation method. Basically, instead of grounding the electrodes for applying basically the electric field across the switch, we're actually applying a voltage equal to the threshold voltage minus whatever swing voltage you want to achieve. Right? Of course, you can't, if you have a threshold voltage of 50 volts, it will be very hard to have a swing voltage of 10 millivolts. That the body bias has to go down, and that's why we're going to pursue scaling. So if you have if you less than 1 volt of body bias, then you can think about maybe 10 millivolts of switching. So in this case, effectively, it corresponds to effectively pre-biasing the beam or pre-stiffening the beam in a way. It's like if you were modifying the actual point of operation of your switch, you were offsetting it, and then you were swinging up and down with this lower threshold voltage. And that is the only voltage that effectively is consuming power, right? Because that's what you're using to charge and discharge your capacitor. So you're effectively offsetting. You're operating around an offset. So the fab process, I'm just going to go briefly through it. It's a relatively simple fabrication process. It's based on deposition and etching of aluminum nitride layer metals. The only thing that I want to point out is that in the community, actually, even in the MEMS community, is aluminum nitride has been pointed out as an exotic material. I actually personally do not think so. It's a sputter material. It's actually sputtered at temperature below 400 C. It's CMOS compatible. And actually, at least in the field of RF MEMS, in the resonators in which I'm also working, is practically probably the best material for making resonators. And if you own actually a Verizon phone nowadays, there's actually an aluminum nitride MEMS device in it. Right? So effectively, it's sold in billions. Aluminum nitride it's a manufactured material in principle. So it's basically, you can see the two beams with the metal contact released by a dry release process. So we've made devices, as I showed you before the SEM, and one key thing is that we can also use that body bias to actually make complementary devices. And here I show, for example, the response of what we call an N-like or a P-like. There's not really a definition in the mechanical domain of a P-type or an N-type of device. But you can see how we can tune effectively the threshold voltage by simply modifying the body bias. And this is actually the same mechanical switch, the same identical layout. So you can simply modify the body bias voltage and actually get basically a P-type or an N-like. And you can see the extreme linearity of the type of performance. Basically, we're changing the body bias, we're shifting the threshold voltage, and you can transform the same switch from a P-type to an N-type of device. So also we talked about subthreshold slope, and here we recorded, for example, 0.065 millivolts per decade, and a leakage that is extremely low. It's actually about the instrument noise is less than 10 femtoamps because of the air gap. So the individual component has sort of been demonstrated. What is next, right? We wanted to prove that we can actually build a...
Can you comment on the very strange horizontal scale?
Very strange. Well, that's because... Why is that?
Well, does that mean you start at 2.218 volts and then you swing to 2.219 volts?
Mm-hmm. Well, basically that can be compensated by your body bias voltage or whatever you want to do, right? If you want to shift it to a different voltage. Yeah. That was just open type of thing. Basically, you can do it in a normally closed or normally open type of switch where you're dealing with, right? Depending on which way. That was just to highlight basically the few millivolts that you have to move from one to another. So in terms of small-scale integration, the approach, we use a slightly different approach, and this is actually coming from Andre Deon, thinking about how to implement logic with this type of mechanical structure. The fact that we can use basically complementary function just by reversing the polarity of the bias, and then the fact that gate and source and drain voltages are uncorrelated. So what we decided to do is actually use a pass transistor logic that is commonly used actually, but not, basically we don't have the VT drop that you have in a regular pass transistor logic, and basically make the multiplexer, a 2-to-1 multiplexer, as the key building block for making logic. And that allows you to sort of reduce the component counts and sort of reduce also the mechanical delays in an approach practically similar to what the Sujay has already highlighted. So effectively, you have basically your multiplexer. That's the key symbol that we're using to effectively two transistors that are connected. Basically, the two gates connected together, each having a separate body bias, and effectively, very simple. If you have a logic high, you're going to get output, and then vice versa, you're going to turn the other one with a logic low. But the key thing is that now you have availability of 3 terminals. And this is the same schematic of the structure, but basically you can implement different logic functionality basically out of a multiplexer. Effectively, you can build XOR or AND out of the same multiplexer just by simply tweaking around the voltages of your terminal. And you can see that basically in this case we demonstrated with this type of actuator about 1 volt actually type of digital logic. This, I believe, is one of the lowest demonstrated for a mechanical structure. We also demonstrated 0.5 volt actually out of this, some of this multiplexer. And the body biases in this case were in the order of 3 to 4 volts. We've also looked at a half adder type of demonstration. Again, in this case, we 1.5 volts. And we've also looked at sort of very simple implementation of a latch that effectively stores you can see that when the clock is high, effectively latches into the prior state. So effectively an implementation of a very simple latch with 1 volt peak to peak again. So same type of body biases in the order of 3 to 4 volts. And then we also looked at inverter. This is just a very classical implementation of an inverter, actually just stacking, just to basically demonstrate that we can restore the voltages. And you can see that basically 1 volt peak to peak, we can actually demonstrate all the 3 levels of inversion. Of course, I'm pointing out the size of these devices. These are actually pretty big actuators, right? So there's a problem there if you want to really talk about low power. And the problem is the capacitance of these actuators effectively, right? So you can lower the voltages effectively. We haven't really demonstrated what the goal that we're going after. But we cannot really talk about low power when we have those type of gates, basically. So the idea is, how do we do scaling? What are the opportunities with these piezoelectric actuators? And as I told you, we think we can solve the leakage problem. What we want to do is now aggressively scale, basically, the technology. And here we put a comparison on basically with respect to a 7.5 nanometer technology node for 2024. And the idea is to go after extremely low swing voltages. We really want to lower them. We think that that's the key advantage of this technology, basically. Even if the capacitances are higher, you can see that basically we end up with a transistor that has a 1.5, about 3 orders of magnitudes larger than a CMOS transistor. And that's because of the a little bit over the electrostatic approach is because of the epsilon r of the material is 9 with respect to air, which is 1, right? And also because there's some mechanical limit of how small you can actually make the structure in order to make sure that it keeps closing. But the real advantage is that now you're solving that issue of interconnects, right? Basically, now you're switching your interconnects with a lower voltage, and that's where you're saving power in the long term, I think. That is the key approach. Low leakage, and at the same time, low charging, low voltages to charge and discharge your interconnects. So how do we scale? So we've actually looked at a possible approach, and that might not be the only one we're going to be looking at, but this is an idea that is actually being motivated by studies that our colleague Rob Karpik has done on platinum tips via AFM, where we can actually monitor basically a single asperity, making contacts and going off of contacts. So we can monitor the adhesion forces on a single asperity, which is the smallest contact you can think of, right, in a way, and how much force is needed to retract basically that contact to win the adhesion forces. And at the same time, basically, how do we get to make sure that we have no leakage basically when we have a gap, right? So we've sort of set the limit of 5 nanometer. We need to make sure that we can close that gap because we're going to use actually adhesion forces to make contacts because we've recorded with the FM that we can get kilo-ohm resistances just relying on adhesion actually. And then you need to have an actuator that has sufficient force to sort of pull off. And win those, for platinum contacts actually, is about 5 to 10 nanonewton for a single asperity. Of course, if you use lower adhesion forces type of contacts, you can even lower that threshold. So you can imagine, keep scaling if you design and engineer the surfaces that are making contact. And actually, collaborators at Argonne National Labs we are looking also at other type of contact, maybe based on diamond or doped diamond, in which you basically can lower that adhesion forces. So here's some equation of scaling. Basically, we looked at the classical equation of scaling. And what we're telling is that, well, we want to make very thin films because we're going to lower the beam length, basically, based on the constraint of closing the gap. And at the same time, we're going to lower what we call basically, in this case, is half of the breakdown voltage is our body bias. We want to lower that body bias because otherwise we're not going to be able to get that 10 millivolts of control if we don't have a few hundred millivolts of body bias, effectively. But at the same time, you have the other constraint, right, of operating above 10 nanonewtons of force, right? So basically, there's a counteracting of a minimum bending, and at the same time, the idea of keep shortening the beam so that you can get more restoring force. But you cannot make it too short because otherwise you're not going to close the gap. Bottom line is, you want to scale both the gap size and you want to scale the film thickness. These are the two main challenges we're actually facing, and right now we're targeting, in the next year or so, in the next couple of years, targeting basically 25 nanometer thick films with 5 nanometer air gaps. That is something that will give us actuators in the order of about a few femtofarad of capacitance and tens of attojoules if you consider the cell switching over the same capacitance of the gate. So how do we get there, basically? So the first thing is one of the biggest challenges for us is maintaining these piezoelectric properties over such a thin film, right, basically. So we've done scaling. We collaborated also with a company, Teagle, now OEM group, and we looked at how these films scale in terms of thicknesses. The results I showed you before were actually for 250 nanometer thick films. We've also built, I will show you shortly, like 50 nanometer devices, 50 nanometer thick devices. So effectively, what happens is that it's a polycrystalline film. It's not well-oriented anymore, but still maintains, well, not well-oriented, is what we call basically a rocking curve, which is a measurement of the orientation, which is about 3 degrees, but still maintains basically a piezoelectric coefficient that is comparable to the one of a micron film, which we care for making sure that we are actuating. The other problem is stress. So we're looking at ways to sort of minimize the stress in the film. We can control the in-plane stress very well, actually, because that was developed for the cell phone business. These RF filters where you had to control the stress. But with the stress gradient, is still a problem, and we're looking at a way to sort of heat the substrate probably during the deposition of the film to maintain a low stress. The other thing, we looked also at the electrical property of these films. We maintain a similar dielectric constant to the one we recorded in micron scale films, and we also looked at leakage, because the leakage is actually the biggest problem. If you're thinking of using a body bias, effectively you cannot afford leakage. Otherwise, you basically give away all the advantages of that body bias. And for an area of about a centimeter square, basically you get about 0.4 nanoamps at 1 volt bias for 100 nanometer thick film. These are actually very good data points that are encouraging, showing that basically you will have sub-femtoamp leakages for your nano actuators. In terms of making actuators, we looked at 50 nanometer thick films, and these are probably actually the thinnest type of actuators ever made out of aluminum nitride. It's basically, in this case, it was about 50 micron long beam, and we just measure basically by optical profilometer the deflection, and you can see that effectively we can get large deflection with very small voltages, mainly because of the length of the beam in this case. But what's most important is actually the overlapping between FEM prediction and experimental results, which are confirming that these 50 nanometer thick films are effectively having reproducible properties, and they have basically the same piezo coefficient of the same stiffness of micron scale type of films. So this is encouraging. We went ahead and also built basically with this nanofilm 100 nanometer thick aluminum nitride structure, where it basically forms a simple switch. In this case, the actuator is about 50 by 50 micron. And we had some problem with the leakages, but in this case, we still saw the abrupt switching that we saw. In this case, we're monitoring resistance. And again, the ability to tweak that switching voltage by tweaking basically the body bias. In this case, where it was about 6 millivolts. One last note also about the reliability. We run some cycle counts basically on this device. These are actually cold switching in terms of performance, and we reached about 1 billion cycle in this case, with about a mega ohm in this case of contact resistance, which is probably a little high. Probably you want to go a little lower in the under 100 kilo ohm or so. But I'm not talking about reliability because I think it's still an ongoing challenge. It's a problem that basically we need to fully understand, especially at this scale, where basically the current density are very different from the one of regular mechanical switches that is being used for RF MEMS, and especially with new materials. Right? We're using platinum in this case. That's probably not the best material to use for making a good contact. So as a summary of the scaling, basically we looked at different actuators with different film thicknesses. We've seen that we can tweak the threshold voltages because actually we can lower the body bias, right? So we keep scaling, we lower the body biasing, and we can lower effectively. We have more control on that threshold voltage, on the reproducibility of that threshold voltage. We've also measured some of the rise times. Basically, they get faster, clearly, as you make them smaller. And what's encouraging is also, well, we changed slightly the type of contact, but what's encouraging is that by getting the structure smaller, stiffer, higher contact resistance, actually it seems that the reliability, at least in terms of mechanical reliability, because these are cold switching, is actually improving. So it's sort of like an encouraging pathway towards miniaturization. So in terms of summarizing, basically the aluminum nitride, in my opinion, it's an interesting technology, basically, an alternative technology to implement nanomechanical switching. They've shown very low subthreshold slope. They've shown an operation of small-scale integration with 1 volt blocks, some of them operating even with half a volt, basically. And basically, the demonstration of this 50 to 100 nanometer thick films, it's a promising pathway towards miniaturization and towards really producing a low-power solution. Contact reliability, of course, and scaling of the gaps are probably other two key challenges that still need to be overcome in the near future. So with this, I'd like to conclude and acknowledge the people who are working on the project, the collaborators that are working with me on this project, and DARPA for the funding. So I thank you. With this, I thank you for your attention.
Okay, so are there questions for Gianluca? Yeah, Eli.
So
wait for the...
Very interesting piezoelectric actuator, but I'm thinking about your contacts. You had an air gap, but when it made contact, was that like metal-to-metal contact at that point? And so that would normally have a fairly low resistance, but you were talking about 100 kilo ohms. Was that the leakage resistance of the piezoelectric?
No. That's actually the source to drain current. It's just simply because it depends on the amount of force that you're actually applying. Right? So if you don't want to have, it depends on how you design your switch, right? If you overdrive it, then that contact resistance, effective, we did overdrive, right? Basically, we applied directly 6 volts to it, or 7 volts to it, and the resistance was going down to a few kilo ohms. But the point is that there's probably no need to go down to a few kiloohms, right? You can actually just make a design that is sufficient to just make contact, guarantee a low contact, relatively low contact resistance, and then minimize your starting force. The advantage is that it's basically a very linear actuation mechanism. There's no snap-in or anything, right? So you can actually control it relatively precisely at that scale, the displacement.
Is there any hysteresis?
So that's a very interesting question. So we looked at it. We haven't published anything because we haven't done systematic studies. And I think that before having a conclusive statement on that, you probably need to analyze probably at least 50 or 100 devices. But we did see hysteresis in some devices and some other we didn't. We actually do believe that most of the hysteresis is due to the adhesion contact. So basically, it's modification of the contact and so forth. So that's what we think is coming from. So we've seen gaps that are just a few millivolts to gaps that are actually even 1 volt, depending on that. So there's variation that needs to be controlled, actually.
Okay, other questions? Jan, wait for the microphone.
I think in one of your last slides, you showed this switch, I think it was 50 micron or something like that, which had 1 millivolt threshold with a 6-volt body bias. So what's the sensitivity of your threshold to this body bias? If you have any noise on that 6 volt, is it going to be bigger than your threshold?
This was sort of like just pure demonstration. Of course, here you can't operate with a 6-volt bias and have a 1 millivolt threshold. You need to lower the body bias, and that's why we're scaling, right? A 25 nanometer thick film will give you a 400 millivolt body bias. And then at that point, if you think of operating at that point with 10 or maybe the first time maybe with 58 millivolts a swing, then I think you can operate with such a small threshold. Everything needs to be scaled by a factor of 10x.
Okay, any other questions? Okay, I'll ask one question. This one may be the previous one as well. That it struck me when I listened to it that I wasn't sure how a clock would be incorporated into these structures, or if it was necessary. And I just can you answer quickly or is this sort of just asynchronous and things ripple through, or is there some way to kind of control and synchronize so you know when when logic is valid? That computation has been performed.
Well, I think that clocking, I think the Berkeley team has done it. You can build ring oscillators, you can build, you can
I know you can build a clock,
but
can the logic itself incorporate some sort of
Yeah, so
synchronization?
you'll still be doing most likely synchronous systems because there's, let's say, there's the standard trade-offs of doing asynchronous versus synchronous. I think you'll end up in the same regime, and you will do desynchronous things. We didn't actually say anything specifically of how you do it because that is actually somewhat challenging, these mechanical devices. But if people are interested, just feel free to bug us later, and we can show you sort of what we've been working on.
Okay, I'll accept that. Okay, so thank you, Gianluca. All right, so that's it for today's presentations, and I hope everyone will come back tomorrow. I don't have the agenda. What time tomorrow?
Tomorrow, it'll be at
8:30. Okay, but before everyone leaves, I want to remind you that there is a networking reception at the Hearst Mining Memorial Building, and there should be directions to get there. Follow the signs.
Okay.
And I hope to see everyone there.
Thank you.
And Joe?
Because of the weather, the signs will lead you from this building through Corey to Hearst Mining. So they're pretty well posted signs, but I appreciate some of the people from Berkeley to lead some of the outside guests to Hearst Mining.
Okay, how about a hand for everyone presented? Thank you. All right. Thank you.